Chapter 17, probability models. All right, so we have Bernoulli trials. And they meet these conditions. So there can be only two outcomes, success or failure. Meaning like you either got what you want or you didn't. Probability of success is constant. And the trials are independent. Next, we have a geometric model. Which we use when we want to model how long it will take to achieve the first success. There is one parameter, P, which is the probability of success. Then we have the geometric probability with P being the probability of success. X is the number of trials. Until success occurs. Q is 1 minus P, which is the probability of failure. So the probability of X is Q raised to the X minus 1 times P. The expected value is mu, which is 1 over P. And then standard deviation is the square root of Q divided by P squared. So we'll look at an example of this. 91% of emails are spam. How many emails should you expect to open until you find a real message? So our two options are spam or not spam. So we're going to be doing P and Q, and they have to add up to be equal to 1. So we're told that 91% of emails are spam, so that's going to be a failure. Our success is going to be that we get an email that's not spam. So 0.91 is a failure, meaning that it is spam. So then the success is going to be 1 minus 0.91, which is 0.09, which is success, meaning not spam. So how many emails should you expect to open until you find a real message? So we're going to use the formula for expected value. So that's this E of X here. So E of X is equal to 1 over P, which is 1 divided by 0.09, which is equal to 11.1. So basically, there are going to be 11 emails before the first real email. So if we modified this question a little bit and said, what is the probability the fourth email is the first real one? That's going to use this other formula, this P of X is equal to X. So it's going to be Q to the X minus 1 times P. So P of X being equal to 4, meaning the fourth email is the first success. Then we have Q raised to the 4 minus 1 times P, which is equal to Q cubed times P, or 0.91 cubed times 0.09, and that comes out to be 0.0678, or 6.78%. So that's the probability that the fourth email is the first real one. And we'll kind of come back to that problem again in a minute, modifying it a little bit for the next thing. So we also have something called the 10% condition. And so for Bernoulli trials, they must be independent. So one trial should not affect the next one. If they're not, then it's okay to proceed as long as the sample size is less than 10% of the population. This section's going to end up with a lot of calculator functions on them that you have to basically be able to figure out which one you need to use. So I have a few notes here to kind of help with picking that. So, geometric model is on your calculator. So we have a couple options. So geometric PDF, so it's the way it's written is GEOMET and then PDF. And that is for an individual outcome. And so it'll ask for, it'll say something when you type it in. It'll give you like, well, it'll ask you if you, like if it was an order calculator, you would just have to know what to type in, but it'll prompt you for what to type in. But it'll be the probability and then the number of trials, basically. So that's PDF. So then we have geometric CDF. So it's GEOMET CDF. And this is for cumulative success on or before the Xth trial. And it'll make more sense as we do examples for which one you need to pick. So that's geometric model. Next we have the binomial model. And I don't know if I actually, oh yeah, I will have a thing for them in a little bit. So the binomial model calculates the number of successes among a fixed number of trials it still requires Bernoulli trials, and there are two parameters. P is still the probability of success. N is the number of trials. And X is the number of successes. In N trials. And Q is still going to be the probability of a failure. I'm just going to mention that because it's pretty much for the entire rest of what we do in stats, it's going to be P and Q as success and failure. So the probability of X being equal to X is, okay, NCX times p to the x times q to the n minus x. Gracious. Now I'm going to note over here, NCX is combinations. So I don't know if you've ever done anything with permutations or combinations or if you've seen them, but this is combinations. So it's the total number of combinations. Yeah, I don't usually end up having time to get to it. This year I might have time to get to it. It just depends on the year, but it's beneficial. It's the total number of combinations of X successes in N trials. And the formula for it, now your calculator will do it for you, but if you want to do it by hand, it is n factorial divided by x factorial times n minus x factorial. The calculator will use NCR, but I'm using x for the purpose of what we're doing here. But and then our mean is n times p, and the standard deviation for this one is the square root of npq. So I'm going to jump back to that email example. So we had that P was equal to 0.09 and Q was equal to 0.91. So suppose you have 25 messages with N being equal to 25, so that's the total number. What is the mean and standard deviation of real messages? So the mean, we just use that formula. Huh? Oh. All right, so our mean is N times P, so that's going to be 25 times 0.09, and that will be 2.25. Then standard deviation is the square root of 25 times 0.09 times 0.91, and that's 1.43. So then if it asks something like, what is the probability of 2 real messages going to be the probability of x being equal to 2 So we do 25C2. So under the calculator, that's under math, and then there's a thing called probability, and then it says NCR. So 25C2 times, let's see, it is P to the X, Q to the N minus X. So it'll be P, which is 0.09, raised to the 2, and then Q raised to the 25 minus 2, which is 23. Which, if you were going to do it by hand, would be 25 factorial divided by 2 factorial, 23 factorial, times 0.09 squared times 0.91 to the 23rd, which I would pretty much always, you know,
If it's like,
just use the calculator, but
factorials, you gotta go like all the way down each number.
yeah, so like 25 times 24 times 23 times 23, yeah. There is actually a factorial button on the calculator, though.
Oh, there is?
Yeah. Don't remember where it is, but yes, there is. Oh, it's under probability on the calculator. So if you hit math and then you arrow over to PRB, it's probability. It has permutation, combination, and factorial are underneath that. And so, anyways, if you put that in, that's going to come out to be 0.2777. So there's basically a 27% chance that you get 2 real messages in the 25 messages that you started with. So then to the calculator stuff, for if we were just going to put in a binomial or binomial model, the binomial PDF. So there's still going to be a PDF and a CDF for binomial as well as there was for geometric. So binomial PDF function calculates binomial probabilities so binomial PDF of, it'll ask you for N, P, and X, where N is the trials, P is probability of success, X is the desired number of successes, and PDF is going to indicate that it's an individual outcome. So exactly X successes. And then if you had binomial CDF, it'll still be of NPX with them all being the same NP and X that we already wrote down. And this calculates X for, calculates X or fewer successes in N trials. So just something to be aware of, watch out for in wording. Watch out for the phrase at least X. We said with one of the other sections that we did recently that if you see like at least, we should think of the complement. So same thing, if you see at least X, use complements of 1 minus binomial CDF of NP and then do X minus 1 for whatever it wanted. And that removes everything before it. So you say at least X accounts for everything X and after. All right, using the normal model, for binomial models requires checking the success failure condition and by that I mean a binomial model is approximately normal if we expect to see at least 10 failures and 10 successes. So basically, if we multiply n times p, it should be greater than or equal to 10, and n times q should also be greater than or equal to 10. Go back to our example for the last thing to look at this.
Is that an H?
N.
That's an N.
Yeah. All right, so back to our example. So we're going to suppose that you put a spam filter on your email. So your spam filter only allowed 151 of 1,422 messages through. Is it too aggressive? So we check some conditions. 1,422 is less than 10% of all emails. So that's the first condition. The probability of success is constant, so P is constant at 0.09. If we were to multiply n times p and n times q, we would get 1,422 times 0.09 and 1,422 times 0.91. And so those come out to be 127.98 and 1,294.02. Both are greater than 10. So we meet that condition as well. So then we can find the mean, which is n times p, which is 1,422 times 0.09, which we already found up there to be 127.98. And then standard deviation is the square root of n times p times q, which is the square root of 1,422 times 0.09 times 0.91. And that gives us 10.79. So then, check something. If we wanted to see how aggressive it is, okay, we're looking at basically the probability of x being less than or equal to 151, because that's how many it allowed through. We would check this by doing, we want less than that, so we would do the normal CDF for 1E9 or negative 1E99, and then the upper would be 151. Mean is the number we just found, 127.98. Standard deviation 10.79. And when we do that, that gives us 98.34%. So there is basically a 98% chance that no more than 151 are good. So basically, like, it's not too aggressive, essentially. That it's fine. Now, I was going to try one other thing here. Oh, that's not it. We could also test this by using binom CDF without having to have done all this other stuff, because it would have been of the total number of trials, which was 1,422, and then it was .09 for P, and then X was 151. So you could also have done that, and it would come out to be 98.36. So basically the same thing. So 2 different ways to get the same thing, just depending on what you're given and what you decide to find. But we wouldn't have had to find anything to use binom CDF. We had to find something to use normal CDF. But that's all the notes for this chapter.